Welcome to AI Paper Slop, the YouTube series where we summarize AI and tech papers for technical folks who just need to stay up to date. We are jumping straight into a massive breakthrough today. The paper is called Cake, Compiler Agent Co-Designed for Frontier Kernel Evolution by researchers from NVIDIA and Carnegie Mellon University.
Yeah, and the core insight you need to know right up front is that this paper basically solves the massive disconnect between AI coding agents and GPU compilers.
Right. Because historically, when agents try to write GPU kernels, they treat the compiler like a total black box. They guess code, they get a binary pass or fail, and they just tweak things blindly.
Exactly. But Cake introduces this thing called Cake IR. It's a typed hardware-explicit schedule representation where the compiler and the agent actually co-evolve. So the harness gives localized precompiled diagnostics, and repeated agent failures actually become new compiler rules.
Which is insane. And the results are wild. Agent-generated kernels like Kimi Delta Attention hit a 2.05x speedup over official baselines. And their clean start Flash-KMeans beat highly tuned baselines on NVIDIA B200 GPUs.
Yeah, if you are an ML engineer or, an AI researcher, you know exactly how excruciating kernel optimization can be. What Cake represents is a total structural shift. We're moving away from treating the compiler as just this unyielding referee that rejects bad code.
Right, it becomes a collaborator. But to really grasp why this is such a breakthrough, we kind of have to look at why current AI agents just absolutely suck at writing expert-level GPU kernels.
They really do. I mean, think about the current loop. You take an optimization agent, it proposes some code, usually in raw CUDA or maybe Triton, and it sends it to a testing harness.
And then it just runs a benchmark.
Right, it runs the benchmark and gets back a latency number. Or crash log.
It's like trying to beat an incredibly complex video game completely blindfolded.
That is exactly what it's like.
You wander around using the controller, and the only feedback you get is just a game over sound after like 10 minutes of playing. You get zero explanation of which pit you fell into or which enemy hit you. You just have to restart and blindly guess a different path.
Yeah, because the environment completely fails to provide causal feedback. If a kernel crashes, the log doesn't isolate why. Was it a synchronization failure? Was it a hardware contract violation?
Or just a memory alignment issue, yeah.
Exactly. And even if it compiles and runs, getting a single latency number, like say 150 microseconds, that doesn't tell the agent which specific decision caused a pipeline stall.
Right. The agent doesn't know if its memory fetch was too slow or if the math operations were bottlenecked.
Which brings us to the whole domain-specific language dilemma. High-level DSLs like Triton are super popular right now.
Oh yeah, Triton is everywhere.
But it's popular because it abstracts away all the brutal hardware realities of the GPU.
Which is great for humans, but abstracting away those hardware details is exactly what prevents an agent from hitting that peak expert-level performance. Because Triton hides crucial optimization knobs, like warp specialization. And for those who might not live in the bare metal details every day, warp specialization is basically assigning specific hardware threads to highly dedicated tasks. So instead of every thread doing a little bit of memory fetching and a little bit of math,
which is horribly inefficient.
Right. Instead of that, you assign one group of threads purely to fetching data, like prep cooks in a kitchen, and another group purely to doing the matrix multiplication, the chefs.
I like that analogy.
Triton obscures all that choreography, along with memory tier placement, and those are the levers you need to take a kernel from just functional to expertly tuned.
So you might think, okay, if Triton hides the levers, let's just use a low-level DSL like Qt.
Right, just go lower level.
Yeah, because Qt exposes all that granular hardware control. But the trade-off is that it demands this incredibly complex layout calculus. It requires a layout algebra where every memory stride, offset, and tensor shape has to be globally consistent across the entire program.
And this is where the LLM architecture becomes a fatal flaw, right?
Exactly. LLMs are autoregressive. They generate text sequentially, token by token, from left to right. But layout calculus requires top-down, holistic mathematical consistency.
So if it messes up a calculation early on.
Yeah, if it makes a tiny mathematical mistake on a memory stride on line 10, it can't just hold that thought and fix line 50 later. By the time it gets to line 50, the whole global algebraic layout has completely collapsed.
Oh, wow. So it just generates these errors tied to its autoregressive nature.
Right, and when those algebraic errors happen in a low-level language, they're almost impossible for an agent to localize or debug.
So they're just trapped. High-level languages hide the knobs, and low-level languages demand a level of math consistency that a token-by-token generator just can't maintain without hallucinating.
Which is exactly the bottleneck Cake addresses with Cake IR.
Right, because if agents fail because the language is meant for humans, the obvious fix is to build an intermediate representation explicitly for agents.
Yeah, Cake IR is a typed hardware-explicit schedule representation. And the silver bullet here is that it completely removes the need for the agent to manipulate layout algebra.
Wait, really? It just doesn't have to do the math?
It doesn't. The agent makes high-level commitments about scheduling, and the compiler handles all the complex algebraic loring.
Okay, let's break down how this IR actually works,
Yeah.
because there are 4 specific properties they outline. The first is a type-checked vocabulary.
Right. Instead of letting the agent write raw, unconstrained C or PTX code, it has a fixed, strict vocabulary for compute and memory.
Makes sense. And the second property is declared resources, which feels like a massive shift. Because on modern architectures, like Blackwell, you have shared memory spam and tensor memory tmem.
Yeah, and pipelines and synchronization barriers.
Right. And in Cake IR, these resources have to be declared exactly once upfront. The agent defines the shape, the data type, and the lifetime of every memory buffer before it does anything else.
Which naturally leads into the third property, explicit roles. Warp groups actually get names.
Like the prep cooks and chefs.
Exactly. If one warp group is loading data into shared memory, and another is doing the math on the tensor cores, that handoff is highly visible in the IR. It's not some implicit fragile state the agent has to remember in its context window.
And that ties into the fourth, maybe the most magical property, auto-derived metadata. Because the agent uses the vocabulary, the resources, and the roles to declare what to do.
And the compiler figures out the how.
Right.
When the agent says, warp group A will load this tile, and warp group B will do the math, the compiler uses those upfront declarations to calculate the barrier addresses, the phase bits, the tmem offsets.
Which is genius, because by forcing the agent to explicitly state its intent, the compiler can actually run static analysis before generating the CUD code.
Yeah, it stops the blindfolded player before they walk into the pit.
Exactly. The compiler finally has enough structural context to give localized feedback. Instead of just a pass or fail or an opaque crash, it points to the exact mismatch.
Which leads us into the whole compiler talking back aspect of the paper. Because Cake IR auto-derives this metadata, the harness has these precompile gates.
Right, before it wastes any expensive B200 GPU time.
Yeah, GPU time is precious. So the harness checks for synchronization hazards and hardware conformance first. If a producer warp and a consumer warp are out of sync, it halts and points the agent to the exact line of code.
But Cake takes this even further, which is kind of the wildest part of the paper. The compiler itself evolves. The compiler harness is a target of evolution.
Yeah, if agents repeatedly fail, those opaque runtime crashes are analyzed and turned into new verifier rules or static checks.
Okay, I have to push back on this for a second. Because if you're an ML engineer listening to this, the idea of an AI agent changing the compiler rules should terrify you.
Oh, absolutely.
Like, if the compiler is constantly mutating based on an LLM's failures, doesn't that risk breaking everything? How do they not just create this messy, hallucinated, unstable compiler?
It's a totally valid fear, but they designed a highly defensive, test-gated validation process to stop that. It's not just indiscriminate mutation.
Okay, so how does it work?
There are two paths. The first is agents looking at production kernels and new hardware docs to propose support for new instructions. The second path is analyzing the agent's own crashes.
Right.
But, and this is the key, a proposed verifier rule can't just be merged. It has to pass regression tests across a massive validated kernel corpus to ensure it didn't break anything else.
Oh, okay, so it has to prove it works on existing code.
Exactly. And it has to pass through human-verified merge gates. So an opaque crash today becomes a permanent, stable guardrail for all future agents.
Wow, so the evolution isn't random, it's just systematically abstracting past failures. And what's crazy is that Cake IR itself was built bottom-up this way.
Yeah, they didn't just sit in a room and invent the syntax.
Right. They fed agents a huge corpus of production kernels, asked them to find patterns, and the agents continuously proposed IR updates. The language grew organically.
It's this compounding loop. Tighter guardrails mean the agents don't get bogged down in syntax errors, so they can explore much deeper optimization schedules.
Which sounds great in theory, but, ML engineers only care about one thing. Does it make the GPU go brr?
Always the bottom line.
So let's look at the B200 benchmarks. They ran this clean start Flash-KMeans test. They gave the agents an 80 million token budget and told them to find the optimal kernel.
And no access to low-level target implementations, right?
Right. And using CakeIR, they had a median 1.144x speedup over the highly tuned Flash-ML Triton baseline.
It's huge.
But the control group, the agents writing direct CUDA and PTX, they only hit 0.928x. They actually regressed. And CakeIR hit its peak in 3 out of 3 runs. The CUDA agents went 0 for 3.
Because direct CDA agents just wander into that massive state space, hit silent failures, and can't recover. CakeIR systematically guides them.
And it gets even crazier with frontier kernel synthesis.
Oh, the KDA results.
Yes. Kimi Delta Attention. There aren't massive open source libraries for this yet. And the Cake agent generated a KDA prefill kernel that hit a 2.05x geometric mean speedup over the official Flash KDA across 6 different B200 shapes.
Doubling the speed on frontier hardware without human intervention. That is just monumental.
It really is. And then there's the AlphaMo mega kernel rewrite. This kernel was highly tuned for the Hopper architecture. The agents had to rewrite its W8A8 megakernel for Blackwell.
And they didn't just port the logic.
No. They fused the routing, the projections, the activation functions, everything into one single device program. And it got a 6.204x API-level speedup over the TensorRT-LM baseline.
Which proves something incredibly important about Cake. It shows that architectural schedules can survive and transfer even when the underlying physical GPU instructions completely change.
Because Blackwell handles tensor memory way differently than Hopper, right?
Completely differently, entirely new TM instructions. But because Cake decouples the high-level intent from the low-level execution, the scheduling intent ported cleanly.
The agent and the compiler handled all the new hardware-specific lowering.
Exactly. Usually when NVIDIA drops a new architecture, human engineers spend months handwriting new kernels. Cake basically automates that transition.
And it matches or beats human experts on known workloads, too, like hitting a 1.27x speedup on MQA indexers. But okay, let's talk about production.
Right, the real world.
Because every engineer working on PyTorch libraries knows that a kernel tuned for one exact batch size is just a neat lab trick. If a user passes in a sequence length of 129 instead of 128, the kernel can't just crash. It has to generalize.
And Cake handles generalization as an entirely separate stage.
Which makes sense because if you try to score the agent on broad shape coverage during the initial tuning, you dilute the signal.
Yeah, the agent would just favor safe, mediocre schedules over aggressive ones. So instead, Cake finds highly tuned seeds for specific shapes first.
And then it groups those successful seeds into shape buckets, produces shared variants, and puts guards behind a safe fallback.
But they enforce strict ML hygiene to prevent evaluation leakage. The shape domain is declared up front, so you aren't tuning the dispatcher on the exact same shapes you use to test it.
And the generalization results are solid. On GB200, the dispatcher-inclusive performance for Can-N build hit 1.418x across 112 shapes. K-means hit 1.803x across 124 shapes.
And mathematically correct outputs across all of them. But the real reason this matters for production is code maintainability.
Right. You don't want 500 mutated kernels for 500 batch sizes.
Exactly. That would be impossible to audit or debug. Cake forces the system to reuse a single physical schedule across as much of the shape domain as possible. It prevents routing complexity unless a domain strictly requires a material change.
It's structured discipline generation.
Right.
So to wrap this up, the paradigm shift here is massive. We are moving away from treating the programming environment as a fixed referee. Cake proves that if you give agents the right IR and let them help shape that IR, you get insane performance gains on frontier hardware.
We aren't bottlenecked by human engineers deciphering layout algebra for new tensor cores anymore. The new bottleneck is just how well we define the hardware rules and let the agent search the space.
Which leaves you with a thought to mull over. Think back to that blindfolded video game analogy. Cake gave the AI a specialized way to see the environment, not through human code, but through explicit roles and declared resources.
Yeah.
So if AI agents are now capable of driving the evolution of the compilers and the intermediate representations they use to code,
how long until human-readable code is entirely obsolete?
Exactly. If the IR of the future is optimized purely for an AI's reasoning process, will we soon see programming languages that are mathematically perfect for GPUs but completely incomprehensible to human engineers? Are we basically building the last languages we will ever truly understand?
It's a profound shift. The foundational code of our systems might just not be written for human eyes anymore.
Definitely something to think about the next time you're wrestling with a CUDA memory layout error. Thanks for joining us for this deep dive on AI paper slop. Stay curious and keep building.